Okie doke. All right, Chemistry 3111. This is Chapter 24, Carbohydrates. And before we can even get started on this chapter, it's probably useful for you to review some already. For example, being able to draw a chair conformation. We're going to spend a lot of time looking at chair conformations in this chapter. Remember that we spent a lot of time drawing cyclohexane chairs that, oops, I don't know what's going on with my Apple Pencil, that look something like this. Okay, that's not a very good drawing, but you get the idea. Or, you know, that look like this. And what we're going to do is we're actually going to be spending a lot of time drawing this conformation of a chair, but we're going to be drawing it such that we have an oxygen. So we're going to be drawing sugars, and they're going to have an oxygen in the top right corner of the molecule. Now, again, that's not my best chair ever, but that six-membered ring is a pyran ring, is what we call it, a pyran ring, and we're going to be looking at several pyran rings throughout this chapter. So drawing chair conformations, projections. So the Hogwarts projection of that six-membered ring, that pyran ring that I showed you, would look like this, where we have an oxygen in the top right corner, like that, the Hogwarts projection. You might remember that we drew kind of the shaded bonds like this to show the three-dimensionality of the structure. It's not really my best artwork here, is it? All right, something like that. Anyhow, what else? Fischer projections. So you remember Fischer projections? We looked at those when we discussed stereochemistry. So we're going to look at a lot of Fischer projections. For example, if you have a CH2OH at the top of a Fischer projection and an aldehyde at the top, and if you have a hydroxyl on 1 and then 3 and then 4, and then you put another hydroxyl here and you fill out the rest with hydrogens like this. This molecule has a name. It's the most abundant carbohydrate on the planet Earth. It's D-glucose. D-glucose. So that's a Fischer projection. Also acetals and hemiacetals. So a hemiacetal, that was when we had a carbon with a hydroxyl and an OR group like that. That's a hemiacetal. And an acetal is when we had two OR groups attached to our carbon like that. And then reduction of aldehydes and ketones. So using things like sodium borohydride as a reducing agent. So all things you need to be familiar with in order to, kind of get through this chapter. There we go. Okay, so let's move on to the next slide. It says carbohydrates, or sugars as they're commonly called, are polyhydroxyaldehydes or ketones. If you think about the word carbohydrate, that's kind of a historical word, and where that word comes from is if you look at the formula of glucose, which is C6H12O6, you can think of it as being a hydrate of carbon. All right, we have 6 carbons, and then for each one of those 6 carbons, we have 6 water molecules. Now that was originally what was thought is that carbohydrates were hydrates of carbon. Once their structures were elucidated, that kind of went by the wayside, but the name stuck. So a more accurate description of what carbohydrates are is that they are polyhydroxy, meaning more than one hydroxy, aldehydes, and ketones. And carbohydrates are synthesized in nature from carbon dioxide and water, and that process is called photosynthesis. I remember learning about that in the 3rd grade, and my teacher said, okay, well, the leaves take carbon dioxide, and then they take water and sunlight, and then they make sugar from that. She didn't say glucose, but we end up producing a sugar from that. And so if you think about all the energy that we use to power the human body, an organic chemist looks at the human body as just a big combustion chamber, right? We consume food, and then we break that food down, and we release energy and heat while we do that. But where do we get those compounds from? Well, if you trace the origin of all the foods that we eat, really, when you boil it down, they all come from the sun, right? That energy originally comes from the sun. So anyhow, and when you produce a sugar like glucose from carbon dioxide and water, it's got a lot more carbon, hydrogen, and carbon-carbon bonds than are found in CO2 and water. There are no carbon, hydrogen, and carbon-carbon bonds in CO2 and water, and so you end up with higher energy bonds, and that's why we can extract the energy from glucose when it's synthesized from carbon dioxide and water in the photosynthesis process. Well, let's talk a little bit more about the structure of carbohydrates. And the simplest carbohydrates, we call those monosaccharides. So monosaccharides, another name for those would be simple sugars. For example, two sugars that you might have even been aware of before you took this class or before you read this chapter are glucose and fructose. And if you've ever heard of sucrose, which is table sugar, you might be aware that sucrose is actually a disaccharide, and it's actually made from glucose and fructose coming together. And we'll look at the structure of sucrose later on in the class. But again, monosaccharides are the most simple sugars, but they can contain multiple chiral centers. And in order to keep track of all those chiral centers, Fischer projections are often used to represent their structure. Now, the reason why we're going to look at so many Fischer projections in this chapter is because really when you boil it down, Fischer projections are just simpler, okay, for looking at sugars that have so many chiral centers. I can even help you out with this glucose molecule. We have a chiral center here, another one here, another one here, and another one here. If we go back a slide and we look at the structure of glucose when we have all these dashes and wedges, so this is the exact same thing that we were just looking at on the last slide, okay? But this is using dashes and wedges, and it's actually much more complex to look at the structure using dashes and wedges. And when we try to evaluate the stereochemistry at the chiral centers. And what you're going to see is that I'm going to prove it to you that elucidating or determining the configuration of chiral centers in Fischer projections is actually much easier than using dashes and wedges. So that's why Fischer developed the Fischer projection. I know I told you that in the stereochemistry chapter, but that's a long time ago. So the whole rationale behind Fischer projections is it's actually much easier to keep track of the chiral centers in a sugar. Another thing that you might find interesting is that glucose, which again, the most abundant carbohydrate on Earth, the most abundant monosaccharide on Earth, this is called the open chain form, right? You can see there's no cyclic structure in here. Okay, it's open. It's just a long chain. Well, this actually exists. If you have a solution of glucose, this open chain form only exists around 0.01% of the time. If you're like, well, if it only exists a little bit at the time, why would you draw it like this? Again, because it's very easy to keep track of all the chiral centers and just easier to keep track of the structure that way. All right. Anyhow, let's talk a little bit more about glucose and fructose and how you would, describe these molecules. How would you compare these molecules, and what descriptors could you use to identify these molecules? Well, you probably noticed that at the top of glucose, there was an aldehyde. And when we have an aldehyde at the top of our molecule, we call that an aldose, okay? So this is an aldose. And when we have a ketone towards the top of our Fischer projection, we call that a ketose. Now, notice that I'm not talking about this hydroxyl at the top here. I'm talking about the most oxidized carbon at the top, okay? And the most oxidized carbon at the top are the ones that have carbonyls. So an aldose and a ketose. Can we use other descriptors to differentiate between aldoses and ketoses? Yes, we can, based on the number of carbons. If you look at the number of carbons in this aldopentose right here, we have 1, 2, 3, 4, 5. And so that's where the pent comes from, pent meaning 5. So we use the terms di, tri, tetra, penta, hexa, hepta to indicate the number of carbons. So not only is this compound an aldose, I could say it's an aldopentose because it's got, 5 carbons total. If I look at my ketose, I would say it's a ketohexose. Why? Because it has a total of 1, 2, 3, 4, 5, 6 carbons like that. So an aldopentose, a ketohexose, and if you're wondering, could you have a ketopentose and an aldohexose? Of course, okay? But you have to know how to differentiate between an aldose and a ketose and how to count the number of carbons. So you're already seeing, hey, I can definitely count the number of carbons in a molecule. No problem there. Okay, well, if we look at the simplest possible aldose that we could have, okay, glyceraldehyde is the name of that aldose, and it's shown right here, glyceraldehyde. Okay, now that simplest possible aldose, glyceraldehyde, has one chiral center, doesn't it? Chiral center right here, and you can see that chiral center right there. First question I'm going to ask my students this morning is, I want you to tell me what's the stereochemical configuration of the chiral center on plus glyceraldehyde. Just tell me, is it R or S? I'll give you a second to think about it. And if anybody could just answer, that's fine too. This would be a great question for a final exam. What's the stereochemistry at this chiral center? Okay, somebody says R. I think they're in the right vein. Yeah. Let's see. Okay, I'm seeing some R's. Well, let's evaluate it. Remember that the hydroxyl is going to take priority 1 because it's got an oxygen directly attached to it. If I look at this carbon, it's attached to oxygen, oxygen, hydrogen, whereas this one is attached to oxygen, hydrogen, hydrogen. So this oxygen will be the tiebreaker. This is going to be the second highest priority group. This will be the third highest priority group, and obviously hydrogen is the lowest priority. If we follow those prioritized numbers going from 1 to 2 to 3, going around our chiral center, you see that that's counterclockwise, which would be S. But since our hydrogen is in the horizontal position, which means that it's coming out, right? Well, we're going to reverse that stereochemical configuration, and so it will be R. So whoever said it was R is completely correct. I'm going to erase all this spinach here, okay? So this has an R stereochemical designation, and then negative glyceraldehyde or minus glyceraldehyde must have an S stereochemical designation in that chiral center. Well, if we take R glyceraldehyde, D-glyceraldehyde, which is positive, what does the positive mean? It means that it rotates plane polarized light in a clockwise direction, right? It rotates it to the right, okay? Whereas negative glyceraldehyde, what does that negative mean? It means it rotates plane polarized light in the opposite direction, in the counterclockwise direction. Okay, now when the hydroxyl, okay, says the D sugars, where does this D come from? When the hydroxyl group at the chiral center furthest from the carbonyl is on the right-hand side, okay, we call that a D sugar. And if you're like, I'm not 100% sure about this, okay, well, let's look at these 3 sugars that are down here. You see that they're all prefixed with the letter D. D-ribose, D-glucose, D-fructose. Where does that D come from? Okay, we look at the carbonyl. Here's the carbonyl in all 3 of them, okay? And then we look at the chiral center furthest from that. You always start numbering from the top. So we have 1, 2, 3, 4, 5. This is not a chiral center. Carbon 5 is not a chiral center because that carbon has 2 hydrogens bound to it. But carbon 4 is a chiral center, isn't it? So since the hydroxyl is on the right-hand side, this is going to be a D sugar. The same thing applies to glucose. 1, 2, 3, 4, 5, 6. The 6th carbon is not chiral because it's got 2 hydrogens attached to it, but the 5th carbon is chiral, and the hydroxyl is pointing to the right. And so it's D-glucose, and the same rationale applies to fructose. 1, 2, 3, 4, 5, 6. 6th carbon is not chiral. 5th one, however, is chiral, and it's the furthest chiral center from the carbonyl group. And so these are all D sugars. Now, recall that dextrorotatory versus levorotatory does not correspond to D and L designations. So when you see D sugars or L sugars, it doesn't, if you see a D sugar, it doesn't necessarily mean that the plane polarized light is going to be rotated clockwise like it does for glyceraldehyde. And if you're a little bit confused, let me straighten this out. Okay, let's go over it very slowly. Glyceraldehyde is the simplest possible aldose. Okay, we're just talking about this molecule right here. It just so happens that D-glyceraldehyde rotates plane polarized light in the positive direction. Okay, so D-glyceraldehyde does rotate plane polarized light dextrorotatory. However, what does D mean when we looked at all of these sugars down here? Did it have any, is there anything in here that says anything about plane polarized light? No, it didn't have anything to do with that. When we look at other sugars, so anything that's not glyceraldehyde, what does the D refer to? The D only refers to the chirality of the last chiral carbon. And if the hydroxyl is on the right, it's D. Just because you have a D sugar doesn't mean it's going to rotate plane polarized light dextrorotatory. Okay, that only applies to D-glyceraldehyde or L-glyceraldehyde, effectively. Here are 2 examples. if you look at D-erythrose and D-threose, okay, they're both D sugars. Why? Because the hydroxyl on the chiral carbon that's the furthest away from the carbonyl, or the most oxidized carbon, is on the right-hand side. So they're both D sugars. But look at how they rotate plane polarized light. They both rotate it in a counterclockwise direction. So to rehash, D sugar refers to the configuration of the furthest chiral center. And that the chirality is going to be R. We'll look at that in a second. We're going to get some practice on that. Okay, whereas L sugar has the configuration at the furthest chiral center. The only time that for sure D and L line up with dextrorotatory and levorotatory is with glyceraldehyde. That's it. Okay, so you kind of start at glyceraldehyde and you work your way down from there. All right, well, let's get some practice in designating chirality of some asymmetric centers here. So 24.3, it's kind of a lengthy question here, isn't it? It says determine whether each of the following carbohydrates is a D sugar or an L sugar and assign a stereochemical configuration for each chiral center. After assigning the configuration for all the chiral centers, do you notice any trend that would enable you to assign the configuration of a chiral center in a carbohydrate more quickly? Well, let's start with this sugar here in A. So we'll start with A. And the first question I want to ask you is this a D sugar or an L sugar? Who could answer this for me? Not a trick question. Yeah, it's a D sugar. Why do we know it's a D sugar, Sean? Because if you look at all the carbons, 1, 2, 3, 4, 5, 6, the last chiral carbon, the hydroxyl, is on the right-hand side. Therefore, this is a D sugar. Okay, good. Now we want to start assigning the stereochemical configuration to all of these chiral centers. Let's take a look at the first one. So we'll start with this one right here. Our hydroxyl is going to be number 1. Our hydrogen is going to be number 4, lowest priority. If we look at the two other carbons that are attached, this carbon is attached to oxygen, oxygen, hydrogen, whereas this carbon here is attached to oxygen, carbon, hydrogen. This will be the tiebreaker, the second oxygen. So that means that the carbonyl carbon is going to have the second highest priority, and then this carbon is going to have the third highest priority. If we follow those numbers going from 1 to 2 to 3 around our chiral center, we would see that that is R, right? It looks like R, but remember the hydrogen is horizontal, and so we reverse that. And thus, the stereochemical configuration at that chiral center is what? It's going to be S. Okay, so we figured out the first one. You're like, this is a lot of work to figure all these out. Well, you get faster and faster at it as you go, right? So let's look at the second chiral carbon, this one here, our highest priority, our lowest priority. If we look at this carbon here, you can see that it's attached to oxygen, carbon, hydrogen. This carbon is attached to oxygen, carbon, hydrogen, so we have no tiebreaker. We go to the next one. This one is attached to oxygen, oxygen, hydrogen, and this one is attached to oxygen, carbon, hydrogen. Here's our tiebreaker. It's a lot of scribbling to figure out a tiebreaker, isn't it? Yeah, it absolutely is. This is why scratch paper is so handy for organic chemists. So that means that all of this group here, right, is going to be the second highest priority. Okay, so we'll put a number 2 here, and then we'll put a number 3 here. If we follow that, we go from 1 to 2 to 3, which is clockwise, which would be R. But remember, our hydrogen is horizontal, so we reverse that. So that gives us a designation of S. Let's scribble that down. S is our designation there. Give the next one the old college try here. We've got the hydroxyl, which is going to be number 1. We've got the hydrogen, which is going to be number 4. If we look at this carbon here, it's attached to oxygen, carbon, hydrogen. And this one here is attached to oxygen, carbon, hydrogen. So then we keep going, and what we find is that if you keep going, and I'm not going to explain it for every single one, okay, it's a lot of work to explain every single one, and we've looked at chirality several times, what you see is that this group is going to be the second highest priority, right here, and then this group is going to be the third highest priority. So we go from 1 to 2 to 3, which is S. But remember, since our hydrogen is horizontal, we reverse that, and so the stereochemical configuration will be R. Did anybody go ahead and figure out the stereochemical configuration of the last carbon? Can anybody do that? I'll give you a minute to try to figure out the last one. Yeah, I see that people are already answering, and the answer is the last one is R as well. Now, it takes a lot of time to go through all of these. Let's try one more quick example. We'll try this one over here since there's only 2 chiral centers, so we'll go over it kind of quickly. If we look at the first chiral center, highest priority, fourth highest priority here. This one is obviously going to be second highest priority. We got oxygen, oxygen, carbon, and here we would have, on this one, we would have oxygen, carbon, hydrogen. So if we follow this around, we go from 1 to 2 to 3, which is S, but our hydrogen is horizontal. And so the stereochemical designation there is going to be R. So let's scribble that in. We have an R stereocenter here, and let's try this one. Okay, we have oxygen, first priority, hydrogen, last priority. We have, this group is going to take second highest priority. This one will take third highest priority. We go from 1 to 2 to 3, like that. That would be counterclockwise, it would be S, but our hydrogen is horizontal, and so this is R. This is R. There we go. All right, so if we zoom out now and we take a look at what we've done so far, do you notice any trends that would enable you to assign the configuration of a chiral center more rapidly? I would say yes. Whenever the designation is S, okay, the OH or the hydroxyl is on the left-hand side, and when it's R, the hydroxyl is on the right-hand side. There you go. My students are always on the hunt for a trick, right? Looking for a trick. So if you look at this molecule here, all of the hydroxyls are on the right-hand side. So this one is R, this one is R, and this one is R. All right, give me a thumbs up if you feel more confident in assigning stereochemical configuration at a chiral center in a Fischer projection now. Something that we looked at a little bit in chapter 5, but it never hurts to review those kind of concepts, especially in sugars which have multiple chiral centers. A little more complicated. Okay, great. Well, let's get back to our aldoses for a second here. And if you think about an aldotetrose, okay, an aldotetrose, since we have our aldehyde at the top, right, it's an aldose, and since we have our CH2OH on the bottom, what does that leave us with? That leaves us with 2 chiral centers. So an aldotetrose, any aldotetrose is going to have 2 chiral centers. Now, how do we figure out the number of stereoisomers? Well, this is also something that we looked at way back in chapter 5. The number of stereoisomers is going to be 2 to the power of n, where n is equal to the number of chiral carbons. So 2 to the power of 2 in this case is equal to 4. So that means there's 4 possible aldotetroses, 2 of which are shown here. Okay, 2 are D sugars, and the other 2 are enantiomeric L sugars. We have D erythrose and D threose. The enantiomers of the above compounds are called L erythrose and L threose. If we wanted to draw, let's say we wanted to draw L erythrose, what would we do? Okay, how would we draw the enantiomer? Very simple. Okay, we're going to start by drawing the skeleton. Draw it the best I can. Okay, we're still going to have our aldehyde at the top. Okay, that's not chiral. We're still going to have our CH2OH at the bottom, but what are we going to draw for the 2 chiral centers? We're going to draw their mirror images. So we're going to have a hydrogen here and the hydroxyls on the other side like this. So this would be L erythrose. L erythrose like that. And you could try drawing L threose as well. And you could even look that up, but there's some exercises that we have in the chapter that get you some practice in drawing enantiomers. If we go to an aldopentose, so what's an aldopentose? It's got an aldehyde at the top. You see all the aldehydes here, so it's an aldose. And why is it a pentose? Because they all have 5 carbons. 1, 2, 3, 4, 5 carbons each. Well, in an aldopentose, I have a total of 3 stereocenters. So if I use my formula that I saw before, which is 2 to the power of n, where n is the number of stereocenters, 2 to the power of 3, or 2 cubed, 2 times 2 times 2 gives you 8 possible stereoisomers. 4 of them are going to be D sugars. If you're wondering, like, why, Mr. Dean, why are you so hepped up on D sugars? I notice that you just keep putting D sugars everywhere. The reason why is because D sugars are the sugars that are found in nature. They're naturally occurring sugars. L sugars, generally not found in nature. These are sugars that are synthesized in a lab by chemists. Now, if you've studied amino acids at all, and we're going to look at those in the next chapter, and you'll look at them a lot in biochemistry, the naturally occurring amino acids are actually L. So L amino acids are the naturally occurring amino acids, whereas D sugars are the naturally occurring sugars. Make sense? All right. It's a little bit annoying, things like that in chemistry, but that's just the way it is. Okay, so D sugars are the naturally occurring sugars, and that's why I'm so focused on D sugars. I also want to draw your attention to something that I posted in the chat this morning. The very first thing that I posted says Chapter 24, Aldoses and Ketoses. It's pretty handy to have that with you while you're studying. I'll post it again in the chat right now, so that you, because you don't have to memorize the structures of all the aldoses and ketoses. However, I think it's a good idea to have the structure of D-glucose down, and we'll look at that structure on our next slide, I think. Okay, so if we go to the aldohexoses, there's a typo in here. There's no such thing as an aldohexose. Okay, it's an aldohexose. Anyhow, the aldohexoses have 4 chiral centers. So if we have 2 to the power of 4, that equals what? 16 possible stereoisomers. But 8 of them are D sugars. Why do we know that these are all D sugars? Because if you look at the hydroxyls on the last chiral carbon, they're all pointing to the right-hand side. They have some really interesting names. D-allose, D-altrose, D-glucose, which again, it's a good idea to know this structure. D-mannose, D-gulose, D-idose, D-galactose, and D-talose. Now, again, if you were to draw the mirror image of these, say, for example, you do the mirror image of this compound, you'd have L-allose. All right, so there we have it. Now, if we look at these all together, all of these aldoses, this is the family tree of the D-aldoses with 3 to 6 carbons. So you could say here, aldoses with 3 to 6 carbons in the molecule. So we start with D-glyceraldehyde. Again, D-glyceraldehyde is positive in terms of its ability to rotate plane polarized light. It rotates it dextrorotatory, or right-handed, or in the clockwise direction, or positive, okay? But then when we look at the other sugars, just because they're D doesn't mean, it doesn't give us any clue as to whether they rotate plane polarized light in a positive or negative direction. So what we do is we keep adding chiral centers as we go from an aldotriose to an aldotetrose to aldopentoses, all the way down to aldohexoses, like that. So again, you can just see that what are we doing? We're just adding more and more chiral centers. And the more chiral centers that we have, the more possible compounds we can have. Okay? Again, just to recap, and I know that you're all perfectly aware of this by now, but since we only have 1 chiral center here, we have 2 to the power of 1, so that means we have 2 possible stereoisomers, D-glyceraldehyde and L-glyceraldehyde. We have 2 stereocenters here, a total of 4 possible compounds, 2D, 2L. Here we have 3 chiral centers. That means we'd have a total of 8 possible compounds, 4D, which are here, and then 4L, which are not shown because they're unnatural. And then down here, we have 2 to the power of 4, which is 16. We have 8 D sugars, and we have 8 L sugars, which aren't shown on here. Remember, these are the D aldoses, I should have put. D aldoses with 3 to 6 carbons. There we have it. What about ketoses? We kind of looked at them quickly at the beginning of the lecture when we looked at the structure of fructose, right? I showed you the structure of fructose, and we said that this was a ketohexose because it has a ketone, and it has 1, 2, 3, 4, 5, 6 carbons. So a ketohexose. Anyhow, this is the family tree of ketoses with 3 to 6 carbons. So we start with dihydroxyacetone. You guys remember acetone? You use it to wash your dishes sometimes in the lab when you have residues that won't come off. This is acetone. So if I put 2 hydroxyls on my acetone, right, if I put a hydroxyl here and I put a hydroxyl here, that's dihydroxyacetone, which is a polyhydroxy ketone, isn't it? It doesn't have a chiral center, but it is a polyhydroxy ketone, so it does count as a ketose. Then if we start adding chiral centers from there, we go from D-erythrose, and we could have L-erythrose, and then down to ribulose and xylose. And then when we look at the ketohexoses, we have a possibility of only 8 of them, don't we, right? Because we have 3 chiral centers, and as we stated on the last slide, 2 to the power of 3 is equal to 8, right? We have 4 naturally occurring ketohexoses, and then we have 4 unnatural L-ketohexoses. Okay, they have some interesting names. D-fructose is important. We have psychose, sorbose, and tagatose. Some really sassy names here, huh? All right, well, let's move on and let's try a question. It says here to draw and name the enantiomer of D-fructose. Now, again, I don't expect you to the structure of D-fructose. I will provide you with some kind of handout with any of the structures that you need. But again, if you even look at our textbook, David Klein says in the text himself, in the prose, he says it is a good idea to have the structure of D-glucose at your fingertips. And we'll look at that several times throughout the chapter. All right, so the first thing is that you would need the structure of D-fructose. Maybe you've already gone ahead and drawn it, but I'm going to put it down here. So we have our CH2OH. It's a ketose, isn't it? So we're going to have CH2OH on the bottom. We have our carbonyl here, so we have a carbon, a double bond to oxygen, and then we have 1, 2, 3 chiral centers. We have a hydrogen here, 2 hydroxyls, like that, and then since we have these ones filled out, the other ones will just be the opposite. Here I have a hydroxyl, and here I will have 2 hydrogens. So this is D-fructose, D-fructose. So if we want to draw the enantiomer of D-fructose, which you can probably already guess is called L-fructose, what are we going to do? We're going to draw the mirror image. You can literally take this molecule, I'm going to copy it, okay, copy, and I'll paste it here, okay? Now I'm just going to erase what was on the end of the chiral centers. That's all I'm going to do, just erase it. And I'm going to reverse all 3 of those chiral centers, and I'm going to be done. So if I'm drawing the mirror image, I'm going to have a hydrogen here, a hydroxyl here, and another hydroxyl here. I fill those out. Where I have a hydrogen, I have to put a hydroxyl, and where I have a hydroxyl, I'll put a hydrogen. There we go. There's the mirror image, or the enantiomer, and this is L-fructose. Okay? Now, if you're really lost, and I doubt there's anybody that's this lost, but I've seen it happen a couple of times. You know, I had a student one time ask me, well, Mr. Dion, why didn't you draw it like this? CH2OH, you know, like draw this as the reflection of that. Well, that's not chiral, okay? That's not a chiral center, so I don't have to flip that around, okay? Not necessary. All right. Anyhow, give me a thumbs up if you think you could draw an enantiomer. If you're like, Mr. Dion, I wish organic chemistry 2 had been more of this, you know? Reversing stereocenters. All right, good. Okay, great. And we haven't even gotten into any reactions yet. We're just talking about sugars, but we're going to look at an intramolecular cyclization on the next slide. So if you look at the structure of a monosaccharide, you might remember that an aldehyde can react with an alcohol to produce a hemiacetal under protic conditions. This is something that we looked at way back in chapter 19, and we looked at the mechanism of it, and we actually went over this in detail, and we said, okay, if you take an aldehyde plus an alcohol, the equilibrium is actually going to lie to the side of the starting materials, okay? And then we might have some ways that we could force the reaction forward. But if you, and we looked at this as well, and we said, hey, what if you had the hydroxyl and the aldehyde in the same molecule? Well, then you'd have an intramolecular reaction instead of an intermolecular reaction, right? And this intramolecular cyclization in this particular compound would produce a cyclic hemiacetal that is what? How many members are there in this ring? There's 6 members, right? 5 carbons and 1 oxygen. Hey, we know that 5 and 6-membered rings are favored, right? This goes all the way back to chapter 4, I think, when we looked at the conformation of cyclohexane. Well, if you look at the hybridization of all of the atoms in this ring, all the carbons are sp3 hybridized. They're all in the tetrahedral arrangement in the chair. And the oxygen is bent in terms of its molecular geometry, but its electron geometry is tetrahedral, isn't it? Because it is also sp3 hybridized. And so the take-home message is this: when we can form a 5 or 6-membered ring, that's going to be favored. And that's why drawing rings, as I mentioned on the first slide of this lecture, is so important in chapter 24. Monosaccharides happen to undergo a ring-closing hemiacetal formation, and we get a new chiral center formed at carbon 1, and we call that the anomeric carbon. Now, when you look at the open chain form of the sugar, this is D-glucose right here. It's not really abundantly clear, why, and this is, if I was talking to somebody on the street, it's not really abundantly clear why this hydroxyl is going to react with that carbon, because that's what's going to happen, right? This lone pair is going to do a nucleophilic attack right here. And you're like, well, why the heck would it be, so they're so far away from each other? Well, if you twist it, okay, if you take that chain and you twist it to look like this, you can see how that hydroxyl on carbon 5 is actually pretty darn close to that carbonyl of the aldehyde. So if we have that in a small amount of acid, what's going to happen is, just like we saw on the previous slide, and just like we looked at in chapter 19, we have our hydroxyl, we have our aldehyde, they're going to react in acid, and they're going to form a 6-membered ring. And this is a hemiacetal. Let me prove it to you. Remember that a hemiacetal is when we had a carbon that had an OR group and it had an OH group attached to it like this, okay? That's a hemiacetal. Well, look, here, carbon number 1 has a hydroxyl and it has an OR attached to it, doesn't it? Okay? Now, a hemiacetal can have a hydrogen here. So this part of the molecule, and you might have to look at it carefully, but this part of the molecule here, okay, that's a hemiacetal. Okay, and we formed our 6-membered ring, the closed form. What's important is that you understand is that this equilibrium right here, okay, that equilibrium greatly favors the cyclic form. So we're mostly going to have this form in a solution of the sugar. The 6-membered hemiacetal ring of the saccharide is called a pyranose or a pyranose ring. Depends on, the day. I might pronounce it as pyranose or pyranose. Anyhow, a pyranose ring, right, which is based off of a 6-membered ring with an oxygen in it that's called pyran. So if we have a 6-membered ring with an oxygen in it like this, we call that a pyran. Now, if we go back to this mechanism here, something I forgot to tell you. If we look at, and just focus on what's happening right here when we have the formation of a hemiacetal. A hydroxyl on carbon 5 is going to behave as a nucleophile. Oh, pairs, can't see them. There we go. It's going to behave as a nucleophile, isn't it? And it's going to attack that carbonyl carbon. But remember, that carbonyl carbon is sp2 hybridized, and therefore it's trigonal planar. And so when that hydroxyl attacks, it can actually attack from like the top face of the molecule, or it can attack from the bottom face like this. Now that's illustrated probably a little more clearly in a second. We'll take a look at it. But anyhow, when you're forming a new chiral center there, again, if the hydroxyl attacks from the top, if the hydroxyl from carbon 5 attacks the carbon 1 carbonyl from the top, the hydroxyl that results at the new chiral center is pointing down, okay? Here they say it's trans to the CH2OH on carbon 5. That's fine, okay? I would just say it's easier to say it's pointing down. If the hydroxyl at carbon 5, if that does the nucleophilic attack from the bottom face of that sp2 hybridized carbon on the carbonyl of the aldose, the hydroxyl is going to be on the top, pointing up, or it's cis to the CH2OH. So I just prefer to say that it's up. Anyhow, that carbon, where you form that new stereocenter, it's got a special name. We call that carbon 1 in that pyranose form of the sugar. We call that the anomeric carbon. Everybody who studies organic chemistry, I promise you that your doctor at one point knew the term anomeric carbon. I don't know about now, but she or he definitely knew that term at one point, because anomeric carbon is, the anomeric carbon is very important in carbohydrate chemistry. Now, if the hydroxyl at the anomeric carbon is pointing down, we call that the alpha anomer. Okay, because the way we describe these two diastereomers is we say they're anomers. Okay, so the alpha anomer is where the hydroxyl is pointing down, and the beta anomer is where the hydroxyl is pointing up. Okay, so alpha is down, beta is up. So you want to see a trick that my students taught me, I don't know, a few semesters ago. They said the way they remembered alpha and beta is like this. They said alpha looks like a fish. Okay. And fish live at the bottom of the sea, so they go down in the water. And the beta looks like, oh shit. Anyhow, it looks like a butterfly, and butterflies are up in the air. Okay. Anyhow, I don't know if that helps, but hey, it's there. All right. Anyhow, where the heck was I? Anomers. So the stereoisomers that are formed upon cyclization are called anomers. They only differ at one chiral center, right? If you look at all the other chirality centers, at carbon 2, it's the same. At carbon 3, it's the same, right? And at carbon 4, it's the same. Okay? The only thing that was different here is the chirality at carbon 1, which is the anomeric carbon. So these two compounds that are shown here, these are anomers of each other. What are they? They're a type of diastereomer, aren't they? Right, but they're they have a specific name in carbohydrate chemistry, and we call them anomers. So the anomeric carbon, and we have alpha, where the hydroxyl is pointing down, and beta, where the hydroxyl is pointing up. I promise you that this is going to be really important. Well, what if we had just a regular old run-of-the-mill solution of glucose? And here they have an abridged version of the mechanism drawn for the formation of the alpha and beta anomers. So here's just, this is just plain old open form of D-glucose shown here at the top. Okay, but in, you know, just even in a little bit of acid, you're going to get an equilibrium, right? You see equilibrium arrows here and here. So we're going to get some of the alpha pyranose, so the alpha D glucopyranose, and some of the beta D glucopyranose. But as I told you before, the open chain form exists less than 0.01%. So you have very little of this in solution. And you're going to have the alpha and beta forms predominating in solution. So again, most what you see in solution is going to be the pyranose forms, or the 6-membered rings. Now the interconversion between these two forms, the alpha and beta form, that has a sassy name. It's called mutarotation. Okay, so interconversion in between alpha and beta. So here's what's happening. You have some glucose, you throw it in water. Okay, there's going to be an equilibration occur. You're going to have very little of the open chain form, only a tiny bit, but you're going to have mostly this and this, these two 6-membered rings. And when those interconvert between, you know, from one to the other, okay, that process is called mutarotation. Okay. Now I've been asked many questions, you know, about the mechanism before in class, and I see that in my notes here that I had some things pointed out. So think about it. Carbons 2, 3, 4, and 5 in the open chain form, these are chiral carbons. This carbon, carbon 1, is not chiral. It's sp2 hybridized. But if you look at the ring form, and this is a Fischer projection showing the ring form. So this is actually a bond, right? This is the bond between the hydroxyl. That's this bond right here, okay? This one right here, that's this big line. Now you've got 5 chiral carbons, don't you? You have, look, you've got 1, 2, 3, 4, 5 sp3 hybridized carbons that happen to be chiral centers, okay? So we go from 4 chiral centers to 5 chiral centers. Mutarotation. Okay, the dynamic equilibrium between the alpha and beta enantiomers, again, we call that mutarotation, and mutarotation is going to be accelerated either in acid or in base. Depending on the sugar, with some sugars, the alpha form is going to predominate, whereas with others, the beta is going to predominate. It's actually very difficult to tell which one is going to predominate. So if you went back here and you said, you didn't mention, what the percentage of the alpha or the beta D-glucopyranose forms are, the reason why is because it's not that easy to tell. Now, it has been established for glucose, obviously, but you can't just look at a monosaccharide and predict what the percentage of enantiomers of each enantiomer is going to be in a solution. All right, let's get some practice with drawing. How would we draw some pyranose rings? Well, remember that we could draw that pyranose ring, as I told you at the very beginning, we could draw it as a Hogwarts projection or as a Cherenkov formation. Cherenkov formations are more powerful. Here it says the word better, but I'd say it's much more powerful because it reveals the 3-dimensional conformation of the ring, where you don't get that information from a Hogwarts projection. But both are going to be important. And something else that I told you is that whenever you're drawing a Hogwarts projection, you're always going to draw it like this so that the ring oxygen is in the upper right position. So this is the upper right position right here. And when you draw the chair form, it's going to be in the upper right rear, okay? So you're always going to draw the chair this way, where it's in the rear, right? It's in the back of the molecule, it's in the upper position, and it's on the right-hand side of the molecule. Now, if you've been wondering, and this would be a very good question, why the heck is D-glucose so special? What makes D-glucose so abundant in nature? Well, if you look at the chair form of D-glucose, and this is D-glucose shown right here, all of the groups are equatorial. You guys remember equatorial and axial? If you don't, you should review that, right? If I was to take this chair form and draw in all the equatorial positions, right, they're going to look like this, this, and this, and this, and this. Those are the equatorial positions. If I was going to draw in all the axial positions, they'd look like this, 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 and this, okay? That's something that you should be able to do. That's something we learned way back, way back in chapter 4. Again, the reason D-glucose is so abundant in nature is because all of the hydroxyls are equatorial, right? Equatorial, equatorial, equatorial. The CH2OH is also equatorial. Now here we have the hydroxyl pointing up like this. Could anybody tell me, is this alpha D-glucose or beta D-glucose? And it's not a trick question. Let's draw in right here. Yeah, since this hydroxyl is pointing up, okay, this is beta D-glucose. All right. I also want to point out that anytime we draw a sugar where the oxygen is in the upper right rear position, we're always dealing with D sugars. Okay, so you can almost make that assumption that we're almost always going to be drawing chair forms or Hogwarts projections, whatever, of D sugars. Let's talk about a Furanose ring for a second. We spoke about Pyranose rings, which are 6-membered rings. Now we're going to talk about Furanoses, which are 5-membered rings. Well, a Furanose ring is a 5-membered ring hemiacetal of a sugar. If you look at the structure of fructose, which is shown right here, fructose equilibrates equilibrates between both the pyranose and the furanose form. So depending on which hydroxyl reacts with the carbonyl, okay, whether it's the hydroxyl at carbon 5, as being shown here, or if it's the hydroxyl on carbon 6, which is what's being shown here, you can end up with a furanose ring or a pyranose ring, respectively, 5-membered ring or a 6-membered ring. If you take fructose and you put it in water, it's going to equilibrate, isn't it? It's going to undergo an equilibration. And what you see is that you actually end up with 70% of the Furanose and only 23% of the Furanose. The rest must be the open chain form. Well, even though the Furanose ring exists in a lower percentage, the Furanose is actually the ring that takes part in most biochemical reactions. And when you study biochemistry, you're going to see several reactions where you have Furanose rings taking part in biochemical reactions. Besides the 23% of the Furanose and the 70% of the Furanose, we have around 5% of the anomer of the Furanose, and we have about 0.7% of the open chain in water. You don't have to have those memorized, but it's just kind of interesting to know that. Well, let's try some practice problems, kind of questions that you could be asked on the next quiz. It says here to draw a Hogwarts projection for each of the following compounds. The first thing that we're going to need if we want to draw beta-D-galactopyranose is we're going to need the structure of D-galactose. I'm going to give that to you. It's in that handout that I had posted in the chat. So let's start by drawing the structure of D-galactose. Try to draw it as neatly as I can. Okay, 1, 2, 3, 4. Like that. So this is D-galactose. Okay. Now we're going to draw the Hogwarts projection of it. The reason why intermolecular reactions are favored instead of intermolecular reactions is because intramolecular reactions form 5- and 6-membered rings, right? Those are going to be much more preferred than forming other hemiacetals that are not 5- or 6-membered rings. So it's the formation of a stable ring that is the driving force of the reaction. All right, so let me show you the quick and dirty way how to draw this. If you look in our textbook, I think he has a skill builder that shows you how to draw the structures, and he kind of walks you through it. I can show you Mr. Dion's patented method. So it's skill builder 24.2. So I'll write that down here. Skill builder 24.2. But I teach this in nursing chemistry, so I'm sure that you can all, figure this out pretty quickly. Let me show you the first kind of trick. And that's whenever you're drawing a Hogwarts projection of a D sugar, you're always going to start with this. And then the oxygen in the top right corner of a 6-membered ring. And if you want to dress it up by drawing the shading in these bonds here, be my guest. If you don't want to do it, that's your business. Okay, land of the free. Okay, after you've done that, the next thing you're going to do is you're going to put your CH2OH. It's going to be up here. Okay, that's step number 2. All right. Then another thing you could do, and the order really isn't that important, but another thing you could do is you could number the carbons 1, 2, 3, 4, 5, 6. Starting at the anomeric carbon, we have 1, 2, 3, 4, 5, 6, like that. Remember, it's this hydroxyl that's going to react with this carbon, right? We're going to get these electrons doing a nucleophilic attack over here. Okay, so now here comes the next part. So you have to have this memorized. Maybe I'll make a copy and paste here. Look, copy it, and we'll paste it. There we go. Okay, so you have to know how to draw that much. Okay, so we'll put that over here. I'll put it in here. No, how to draw that. Just have that down in your noggin. Okay, give your noggin a flogging. There we go. Okay, now with respect to the chiral centers, we're going to form a chiral center at carbon 1, aren't we? There's a chiral center at carbon 2. There's a chiral center at carbon 3. And there's a chiral center at carbon 4. At carbon 5, we don't have to really worry about it because I told you that the CH2OH is going to be pointing up all the time. This is always going to be pointing up. So that means we have to worry about the chirality at carbon 1, 2, 3, and 4. Well, here's the first thing. If it's beta D-galactose, that beta refers to the anomeric center. Okay? That refers to the anomeric carbon. Anomeric carbon, which is C1. And if it's beta, that means the hydroxyl is pointing up. So we can start by drawing our hydroxyl pointing up, like that. All of these groups that are on carbons 2, 3, and 4, whatever is on the right-hand side is going to be pointing down in our Hogwarts projection. Pointing down in Hogwarts projection. So on carbon 2, the hydroxyl is on the right-hand side, so the hydroxyl is going to be pointing down. On carbon 3, the hydrogen is on the right-hand side, so that means the hydroxyl is going to be pointing up. On carbon 4, the hydroxyl is on the right-hand side, so it's going to be pointing down like that. And there you have it, friends. That is beta D. Did I make a mistake here? I'm just looking at what I drew in my answers. I want to make sure I didn't make a mistake. Did I draw the structure wrong? Galactose. Did I draw the wrong molecule? Damn it, I knew it was wrong. I messed up one chiral center. Did anybody notice that? Okay, did anybody notice that I made a mistake in one of my chiral centers? Well, I made the mistake at the very beginning and nobody stopped me. So it was the fourth chiral center in galactose is the opposite of what I drew. So I'll fix it. So the hydrogen is on the right-hand side and the hydroxyl is on the left. Okay, so that means I need to fix my chiral center at carbon 4. Hey, there we go. All right, so I got that. And let's erase this bond too. So at carbon 4, the hydrogen is actually supposed to be on the right-hand side, so that means the hydroxyl is going to be pointing up. Okay, that is correct. Good. Saved it, rescued it. There we go. So this is the Hogwarts projection of beta D galacto D Furanose. Dog in here. Furanose. Pardon my language. Okay. Well, let's do the next one, and the next one I won't screw it up. I won't screw up the Fischer projection. I'll be doubly careful. So alpha D manopyranose. So first we need the structure of D mannose. Okay, you could look it up on the chart that I posted in the chat. You can just draw it the way that I'm drawing it. So 1, 2, 3, 4. And in mannose, we have 2 hydrogens and 2 hydroxyls. Okay, there's nothing wrong with this structure. The structure is perfectly lit. Legit. Okay. Anyhow, I'm going to give you 60 seconds. See if you can draw this. Hey Siri, set a timer for 60 seconds.
Okay, your timer is set for 1 minute.
Yeah. Is it already 9:03? Jeepers. Okay, maybe I should just get cooking here. I know it probably seems to you like I've been talking for an hour, but to me it feels like this has been 5 minutes of talking. Okay, copy. Paste that in here. Come on. There we go. Okay. So anything that's on the right-hand side, all of these are going to be pointing down. All right, this is carbon 1, 2, oh, shut up. 1, 2, 3, 4, 5, and 6. Okay, so in carbon 1, since it's alpha, the hydroxyl is going to be pointing down. On carbon 2, our hydrogen should be pointing down, so our hydroxyl is going to be pointing up. I'll draw it like that. On carbon 3, our hydrogen is pointing down, so our hydroxyl is up. Draw it like that. And on carbon 4, the hydroxyl is going to be pointing down. You know, if you look at the book, if you look at the solutions manual, I can't remember. He might include all the hydrogens too. That's your right, you know, if you feel like doing that. But I like to leave hydrogens out. If you want to throw them all in here, be my guest, okay? As long as you have the right chirality at each center, you're good. You're good from there. Okay, let's try another problem. This is question 24.13. It says provide a complete name for the following compound. So we're going to make, I wrote here in my notes, this is what I wrote down. I put assume that we deal only with these sugars. So, but as I told you, when you have your oxygen in the upper right, this is going to be a D sugar, okay? So this is a D sugar, and you can assume that I would give you some kind of guide, like the handout to figure out, okay? So if we draw, we have 6 carbons. So if we draw our Fischer projection, say 1, 2, 3, 4, we have CH2OH, CHO. Let's number the carbons, 1, 2, 3, 4, 5, and 6. Remember these carbons, 1, 2, 3, 4, 5, and 6. Remember, anything that's pointing down, okay, anything that's pointing down is going to be on the right-hand side of the Fischer projection. So at carbon 2, the hydroxyl is pointing down, and so the hydroxyl is going to be on the right-hand side. On carbon 2, the hydroxyl is pointing up, so it's going to be on the left-hand side. On carbon 4, the hydroxyl is going to be on the left-hand side. And since this is a D sugar, okay, D sugar, the hydroxyl on carbon 5 is going to be on the right-hand side, right? This is because it is a D sugar. Then we fill in all the hydrogens, okay, like that. And then we're going to open up that table, okay? So I didn't post it in my notes, but if you take this structure and you try to match it up with the family of Aldoses, you'll find that this is, did I even write down which one it is? I might have to open it up my own damn self. Let me see here. Where is it? I have it here somewhere. Somebody says galactose. Let me check, David. Yeah, it's D-galactose. Gracias, David. Good. So it's D. This is D-galactose. Okay. I'll just put this bug in your ear. Very rarely do I have students take me up on this, but I teach this content in nursing level chemistry, which is a much lower level chemistry than what we're doing or what you guys are doing in this class. But if you're struggling with, going between a Fischer projection and a Hogwarts projection, you could ask me and I could point you in the direction of some videos on my YouTube channel where I go over this much more, or at a much slower pace, okay? And I even add a couple of steps in there to really kind of help them, massage the content into their brain, so to speak. Anyhow, okay, so in order to do the next problem, which is a good one, it says draw the more stable chair conformation for each of the following compounds. So we got beta D-galactopyranose, blah, blah, blah. Okay, we want to draw the more stable chair conformation of all these. So what you would have to have is you would have to have that handout in order to draw these. So I'm going to start by drawing out the structure of D-galactose, because we're going to start with galactopyranose. So I'll write out the structure of D-galactose, which we had on the last slide, but I'll just scribble it down here quickly. So we've got 1, 2, 3, 4 chiral centers, and D-galactose looks like this. Okay, so again, if you needed this on a quiz, I would give it to you. This is D-galactose. Okay, now you want to draw the more stable chair conformation. You remember how I showed you the Mr. Dion patented technique, patent pending, for drawing Hogwarts projections? Well, here's my patented technique for drawing chairs. Okay, you're always going to do like this. Okay, so you have numbered 1, 2, 3, 4, 5, 6 carbons. Your 6-membered ring is always going to look like this. Okay, it's going to look like this 100% of the time, like that. Now I'm going to get out the pixel eraser, erase a little bit here, and you're going to have oxygen like this. Okay, then in the equal, you're going to have your CH2OH. Okay, so that you have to know. You're going to memorize that. Okay, so let's, come on, man. This thing. What's his name? Steve Jobs. Did he invent this? Anyhow. All right, so this part you have to know. Okay, so let's copy it. Copy. Paste. And this part you just have to kind of have it memorized. And if you do all the practice problems, believe me, it will be stuck in your brain. You won't be able to get it out. Okay, so you're always going to start with this. We're going to number our carbons 1, 2, 3, 4, 5, and 6. Well, if it's a beta D galactopyranose, that means that at the chiral carbon, the hydroxyl is going to be pointing up. So it's going to be up and equatorial like this. Everything that's on the right-hand side of carbon 2 is going to be pointing down. Well, if the hydroxyl is pointing down on carbon 2, down happens to be an equatorial position. If the hydroxyl is pointing to the left, that means it's pointing up on carbon 3. It just so happens that the hydroxyl pointing up at carbon 3 is in the equatorial position, and the hydroxyl in carbon 4 is on the left-hand side, so that means it's pointing up, and up happens to be axial position. And so this would be the chair conformation of beta D galactopyranose. Okay, that's it right there. All right, let's try one more. So I'm going to take this template that I made here, I'm going to copy it, and I'm right here. And while I'm writing down the structure of D-glucose, which again you should memorize the structure of D-glucose. The way I would memorize it is this: is 1, 3, and 4. I don't know why, but I like numbers to memorize anything. So you think about it like this, and then it's got nothing to do with the nomenclature or anything. Okay, this is just Mr. Dion's wacky ways. Okay, the first chiral center, the hydroxyl is on the right-hand side, as well as 3 and 4. Okay, that's just the way I do it. Okay, if you have something that's better, you go with. You do you, okay? So there's my structure of D-glucose, okay? If it's alpha D-glucose, that means that the hydroxyl at carbon 1 is going to be pointing down. On carbons 2, 3, and 4, we have a hydroxyl pointing down on carbon 2. So that means it's going to be in the equatorial position. On carbon 2, the hydroxyl is on the left-hand side. That means it's pointing up, and up is going to be in equatorial position. And the hydroxyl on carbon 4 is pointing to the right. That's going to be going down, which happens to also be in equatorial position. So this is the structure of alpha D glucopyranose. Now, we could take all this here and erase it, and we could draw the structure of beta D glucopyranose really quickly, couldn't we? How would we do that? We would just copy this, what we just drew, copy it, and we're going to paste it over here. Okay, that same molecule. And if I want to draw the structure of beta D glucopyranose, all I have to do is switch the stereochemistry at the anomeric carbon and make that hydroxyl point up, because this is the alpha anomer and this is the beta anomer.